Today we're talking about 3D shapes. However, there's something deeper to that. Apart from what we will learn about 3D shapes today, I will make a surprising connection with analytic geometry, the mainstream geometry of modern math. Let's first talk a little bit about what we know about analytic geometry and just how 3D shapes might have a surprising connection with analytic geometry. What we know by now is points and lines. This is generally what we deal with in middle school. Some of you might be quite familiar with circles as well, and these three elements are basically the fundamental shapes that we are familiar with. But these shapes, apart from the circle, a point can only represent a point on the coordinate plane. A line is a first degree expression. So what about second degree expressions? The circle is one example, but there are a lot of shapes in the coordinate plane or a lot of second degree representations that cannot be summarized by a circle. There are a lot for us to be discovered. And that is where 3D shapes come in. But how exactly? We will examine it in a moment. But before that, we'll first talk about basic 3D shapes knowledge. So since this is an AMC12 video series, I'll first talk about some knowledge you need to have in AMC12 and do some problems. After that, we will dive into this connection and start talking about analytic geometry. To begin with, the most basic type of 3D shapes is simply extending a 2D shape. Recall at first, when we are talking about 2D shapes, you're actually extending a segment. Essentially, what a rectangle is that you're stacking up many segments of the same length all the way upward. So this is essentially what a rectangle is. Then how would you extend a 2D shape? For instance, let's say a circle. Your natural extension is just stack these circles in a 3D space, which is very much analogous to the 1D to 2D extension. In this case, what things can we study about this shape? Previously, we went from lengths to area. Now, of course, you can still find some areas on this 3D shape, for instance, the side area or the surface area. But of course, naturally, you will go from area to volume as well. So we will examine the surface area and the volume in a moment. Of course, there are other shapes. For instance, you can also extend a triangle to something like this. And in that case, where the yellow lines are the lines that you can actually see, and the white lines are the imaginary lines in the back. So there are other types of extensions as well. For instance, when you extend a segment, you have most likely also extended into a triangle, right? A triangle is simply selecting a point on the top, and then you're stacking segments like this. However, each time it's growing a bit shorter, but you're trying to smoothly connect the endpoints of the segment and this point on the top. We can do the same thing for circles for 2D to 3D extension as well. We select a point or the apex directly above the center of the circle and then connect it. So you can imagine this as taking a ray through the apex and a point on the circle and then connecting it. So this forms a new shape. Similarly, you can do the same thing for triangles, like this. So now it is time for us to assign names. In general, a shape that is extended with each layer of the same size is called the prism, where if it has an apex, we call it the pyramid. As for the circle, we have a special name. This is called the cylinder, and this is the cone. These are the shapes that we will study today. Next, it is time for us to find the area, the surface area, and the volume. First, about surface area. The way to go for prisms and pyramids is you just study every single side of the shape, and it, in general, is easy to do. It is not much different from 2D. However, what about the cylinder and the cone? Let's take a moment and study it. First up, the cylinder. The way that we often study 3D shapes is through representing it in some way in 2D. Because in general, when we're trying to draw something on paper, it is often clearer when it is 2D, and when it is 3D, it gets a bit strange and difficult to manage. So let's see how we can expand this into 2D. Suppose we take a line here and cut it, and we only focus on the side of the cylinder, which means imagine this part is empty. So when you cut it, it's going to look like this, where the yellow segments are the segments where you cut the shape, and the white segments here is simply actually the circumference of the base circle. We call this part at the bottom the base. So suppose the circle has a radius of r, then circumference is 2 pi r, and let this be the height, then this is h. So the side surface area of the cylinder is 2 pi RH. And you also know the area of the base circle by the area formula, which I expect you to have learned in middle school. You can easily find the surface area here. As for cones, it can get a little tricky. Again, let's try to expand the side, or at least this surface, because we don't have two bases right now. So it's one base plus the side surface area. So again, we try to cut it. And in fact, you can experiment yourself. When you cut it, it's going to look like this, a fan shape. And the area here, we can represent as theta over 360 degrees of the entire area. Suppose this length, the yellow length here, is L. Then the entire area here would be pi L squared. However, what is theta? Now, remember, there is also a relationship between the radius, 2 pi r, because this is the circumference of the base circle, with the radius of the bigger circle here, which is L. In fact, you can write this segment using the ratio again, theta over 360 degrees times 2 pi L is exactly equal to 2 pi r. So what this means is after some canceling, this term, theta over 360 degrees, can be represented as r over L. So the above expression here is pi r L. And this is the formula for the side surface area. However, you might be asking, what is L? Since generally we only describe it by the height h and the radius r. So what is L? In this case, we use the Pythagorean theorem, because suppose we focus on this line, L. This is the same length, so let's forget about this line for now. So right now, if we focus on the center, O, connect these lines, then what you will discover here is this is 90 degrees, because the apex is directly above the center of the circle. So r squared plus h squared is equal to L squared, and you can find L when you need. And that's all. So this is all we need to know about the surface area. Now let's study the volume. When we look back on this extension, we know that the area of the rectangle is equal to the base multiplied by the height. That's b multiplied by h. In this case, what this means is we're stacking segments of length b to a height of h. This definition makes sense. Similarly, for the cylinder, we're saying we're stacking circles of area S to a height of h. So again, the volume here is simply S multiplied by h. In the previous extension also, suppose we have a triangle of the same height. What would happen? If we take a point here, then we discover that this area is in fact 1/2 of the area of the triangle. And what's even more surprising is the fact that when we change the apex, it doesn't really matter. The area is still the same. In this case, of course, this point is not called the apex, but let's just treat it this way. Then in the extension, we can use this insight to find the volume of the cone. How should we find it? Let's try. First, let's view the cone from the side. So the cone has base area k and height h. Well, how can we find the volume of the cone? Think back on how we found the area of the triangle. We just make this perpendicular line, and obviously, the shaded area is 1/2 of the entire area, and similarly for this. But the argument here doesn't really make a whole lot of sense this time if we move it to 3D, because the shape is way more complicated and you can't really say that it is just 1/2. Such an argument will prove faulty in the end. So how exactly should we find the area? A common way to do this is we should represent the area using what we know. So in this case, the triangle can be treated as several layers of rectangles, etc. And we add up the area of these rectangles, we can have a good approximation of the area of the triangle. And when we make the height of the rectangles infinitely small, then it's exactly the triangle, in fact. So in this case, we can apply the same logic. Suppose we divide the cone into n layers, and let's focus on one of these layers. Suppose this is the ith layer, counting from up to down, and there are n layers total. Actually, let's use slices because we're trying to emphasize that the height is very small. Each slice has the same height, that's denoted as h, and to find the volume of a slice, all we need is the area here. Let's call it small k. So how can we find the area of the base of the ith cylinder? We can use a similarity, because since this is the ith layer, then the total height of the first I slices would be I multiplied by h. So that means by similarity, small k to big K is equal to IH to big H squared, because in similarity, the area must be squared. The ratio of the area is the square of the ratio of lengths. So after that, we have the volume of the ith layer can be written as small k multiplied by h, which is equal to I squared h to the third degree divided by h squared. This is the volume. Let's use small v to represent one layer. Then what we are interested is the sum of the volume, which in fact is h to the third degree divided by h big H squared multiplied by 1 squared plus 2 squared all the way up to n squared, because the only changing thing here is I. And we already know what this expression is. This is n multiplied by m plus 1 multiplied by 2m plus 1 over 6. If you don't know how this happened, go check out my third video of the series. And now it is time for us to substitute n, because we know n is equal to big H over small h. So the above expression can be written as h squared over big H squared multiplied by h over h big H plus small h multiplied by 2 big H plus h over 6 multiplied by h to the third degree. And here you can see these can cancel off. So we simplify to h plus small h multiplied by 2 big H plus 1 small h over 6 big H. And remember, we are taking h is infinitely small. So in that sense, this term doesn't matter, this term doesn't matter, so the expression simplifies down to 1 over 3 big H. And I forgot to multiply a big K here, so this term should move to the right. So what is going to happen here is everything gets a big K. And this, in fact, is 1/3 of the volume of the cylinder that has the same base and the same height. So in this case, we have analogously found that since the triangle is 1/2 the area of the rectangle corresponding to the triangle, so the cone is 1/3 of the cylinder volume that is corresponding. And we are done. So this is a really interesting argument because we're utilizing some infinity. H is infinitely small, but I hope you understood what I'm talking about here. So up till now, this is all we need to know. And of course, in your path down 3D geometry, in the future, you might hear terms like tetrahedrons, cubes, octahedrons, dodecahedrons, and icosahedrons. These are just other shapes that are formed by prisms, pyramids, cones, and cylinders. So now it's time for us to study some practice problems. We're told that we're given a regular hexagon with a side length 6, and to each side there's triangles of length 8 attached. And it forms a pyramid. So we are to find the volume of the pyramid. This is actually just utilization of what we have just learned. So try yourself. You can envision it as this. Since essentially we have a hexagon, I'm not going to draw the full version just so that you can understand what's going on with 8, 8, 6. And to find the volume, all we care about is the base area and the height. The base that we're interested can be found by treating the hexagon as 6 equilateral triangles. So the total area, since one such triangle has area 9 multiplied by square root of 3, so the total area is 54 multiplied by square root of 3. So we focus on one vertex that's marked in yellow, and this vertex corresponds to this point in our 2D graph. Up here, this is the apex, and the segment between them is evidently 8, because this is the apex, this is also the apex. Now, we also need the center. So the center of the hexagon is the blue point, and the distance between the yellow and blue point is evidently 6. And here, all we need is the height, so the height is this length. And it is, of course, perpendicular. Using the Pythagorean theorem, we can easily see this is 2 square root of 7. Then all we need to do is to apply the formula. The volume is equal to 1/3 of the base area multiplied by the height. And that gives our answer 36 multiplied by square root of 21, and we're done. A basic practicing problem. Next up, a problem that requires a little bit more of 3D to 2D conversion. Take a moment and read the problem. So I'm going to directly show you the 3D graph to help you envision what it looks like. And what is going on here is simply you have a triangle and you have a sphere tangent to this triangle. Now, how can we actually make use of this 3D image? We look at it from different aspects and transform it into a 2D shape that we can actually calculate. In this case, when you look down on the 3D graph, you can see that we know all three side lengths of the triangle. Then that means we can find the radius of the circle that we are currently seeing by utilizing the fact that it is inscribed in the triangle. Then we can look at it from this perspective. So this length here is the radius that we have just found, and this is the center. If we take the center of the sphere as well, we already know this larger radius. So that means we can find the distance between the center to the plane, and we have successfully solved the problem. And this utilizes interpreting 3D relationships using 2D images, because all of these are manageable on your 2D draft paper. So you can solve it intuitively by drawing some 2D graphs. That is actually helpful. I won't go into the solving details, but the answer is placed in the Q&A box on YouTube. Next problem. Again, read the problem carefully and try to draw some 2D graphs that you think is helpful. So this is the first one we're interested in, and we haven't talked about what the volume or surface area of the first is. So how should we solve this? We should convert what we don't know into what we know. So this thing resembles a cone. So let's see how can we change it into a cone. We extend these lengths so that they intersect. Now this is a cone. We're given the bottom radius here is 6, and the middle radius is 3. The height of the bottom part is 3 multiplied by square root of 3, so evidently the total height should be 6 square root of 3. Now, I guess it is time for us to expand this. Or, of course, it is possible for you to consider first finding the L. The L in this case is equal to 12 by the Pythagorean theorem. Now we can safely expand the cone, and let's see what it looks like. And yes, it is a semicircle. Let's see why. So first we know the circumradius here is 12 pi, and we also know that up here the radius of the larger circle is also 12. So the semicircle radius should have been 12 pi. Then that means the central angle here is 180 degrees. Now, remember, the problem is saying there's a bug here, and at the opposite side, there's a bug there. On the graph, what it's going to look like is this. So let's see, what is the fastest way to get from this point to the other point? Let's draw a line from this point, and let's see what would happen. Of course, when we want it to travel directly there, it's going to intersect. However, if we just move until we cannot move anymore and travel along the arc, it's going to be a little bit long. So if we move it out a bit until we're at tangent, this is the fastest moment. You can try to prove why. In this case, this length can be easily found. This is 6 square root of 3, and we just need to find the length of this arc. The angle here in the middle is 30 degrees, so what that means is the length of the arc is exactly pi. So the answer is 6 square root of 3 plus pi, and we're done. Next and last problem. We are given a regular octagon. Let's draw it. So we're only showing part of the octagon, but we have already covered A and D. And we know there is an apex. So we're to find the height of the radius. Remember, when we're trying to find the height, we will analyze it using a 2D graph. Again, let the blue point be the center, let the yellow point be A, and let the apex be the red point. So in this case, we have this. First, let's find the distance between the yellow point and the blue point, and we can use some basic trigonometry here. This is 45 degrees, despite my drawing is pretty bad, because 360 divided by 8 is 45 degrees. So we can use the law of cosines. AB squared is equal to 2AO squared. This point is O, minus 2 cosine 45 degrees multiplied by AO squared. Using this, we can solve for AO squared, which is 2 plus square root of 2 over 2. By now, we only need the square values because we're trying to find the square of the height. So the square root of the height, or OV is simply equal to AV squared minus AO squared. So we only need these two lengths. What is AV then? Again, let's think about this 2D fashion. First of all, we can find AD, again using the law of cosine. This time, we have BOD is 90 degrees, AOD is 135 degrees. We also know AO. So it is not difficult to find AD. AD squared in this case is 3 plus 2 times square root of 2. What then is AV squared? Remember, AV is equal to DV, and AV is perpendicular to DV. So what that means is we can draw the points A, D, and V exclusively. AV is equal to DV, and it is perpendicular. So what that means is AV squared is 1/2 of AD squared. So AV squared is 3 plus 2 times square root of 2 divided by 2. AO squared is this. So we know OV squared is 1 plus square root of 2 over 2, and we are done. Congrats! That's all 4 problems for today. And as you can see, as long as we can properly use 2D shapes to represent 3D relationships, it's never going to be too hard. You have 3 more problems for homework, which aren't too hard. And only for the last problem, it is slightly challenging, and my hint is don't be afraid to convert a geometric problem to an algebraic one. Yeah. So now it's high time we talk about how we can relate 3D shapes to analytic geometry in the 2D plane. First of all, the most natural thing to do is to set in 3D shape using a 2D plane, because naturally, only when we intersect it, we can have something that we can study in 2D. So in this case, intersecting these things, like there are too many prisms and pyramids possible, so let's not focus on it yet. As for the cylinder, generally when we intersect it in some fashion, it can be covered by the cone. The cone is going to yield more information and more potential because it is placed in a stranger way. There's angles, there's rays, there's everything. The apex is going to make the difference. So in this case, let's see what we can do. In this part of the video, it's really hard to motivate, but let's just enjoy the beauty of math and the inspiration of mathematicians, and let's just take a look at how they discovered relationships between these shapes. Let's see. What you're currently seeing is 2 cones, one facing upwards and one facing downwards. Apart from that, we also have a plane. And this plane, it has a fixed point, c equals 2. That means no matter what, it's going to pass through the point 0, 0, 2, like this point. As you can see, when I move the plane, there's one point that remains fixed. Also, we have A. In this case, I made A range from 0 to 3. And as you can see, when we move it around, it's going to intersect the pair of cones at different situations, like this. So what is occurring here? Let's look at what happens when it intersects at different situations. When A is equal to 0, we get a circle. Nice. But when we tilt it slightly, we get a egg shape. And what we call this in math is the ellipse. So it is just like a stretched circle. When we move on more, don't worry, it's still an ellipse. We just have to shrink it, and you see eventually it's going to form this ellipse shape again. But eventually, when we move up more until A is exactly equal to 1, in this case, we're using a very basic generating cone. So A equals 1 is exactly 1. The line is parallel to one generator of the cone. So what this means is if we focus on a point here, this point is on the cone, evidently, we just have to connect it with the center. And this is one generator because it is essentially a ray from the origin to any arbitrary point in the space. And what is special about the cone is it is actually a group of ray generators that is all placed on this circle. So that is what is special. In this case, this ray is going to be parallel to the plane because both is 45 degrees. What this means, if I change the definition of the cones here so that the rays are at a different degree, then similarly, the case where it is parallel, it should also change. So what I'm saying is the special thing is not A equals 1. The special thing about this possibility is the plane is parallel to one of the generators. Under this special circumstance, what we're going to look at is this shape. This is actually a parabola, and as for why it is a parabola, we will take a look in a moment. But when we move A, make it even larger, something very interesting is going to happen because we're going to intersect it at the bottom part as well. So essentially, the shape that we're concerned with here is the combination of this thing. We can trace the edge, and it's not going to get quite to the origin, and it's going to move back up again. And it's also the second half down here. So this we call in math the hyperbola. It is not a parabola because it's growing slower compared to the parabola. In this case, as you can see, it's going to get closer and closer to exactly align with the generator. As you can see in this part, if we trace it under this view, it is actually getting very close already. This is what we get when we connect this point on the hyperbola, and this is to the origin. And actually, another point on the cone is located here. So it's actually growing very slowly, almost linearly. So that is what is interesting about hyperbola. And that is an overview of the four shapes we can gain from intersecting a cone. Now let's take a look at what special things is going to occur when we actually intersect it. Let's begin with the circle, because we already know about the circle. In this case, every single point on the circle is going to have an equal distance to the center. Now, let's overcomplicate this and try to prove it in a crazy sense as it is. What we're going to do here is we're going to use a few circles. If we look from the side, what is happening is we have two circles that is tangent simultaneously to the cone and to the plane. Let's call this O1 and O2, call this point F, which is the center of the circle. And these tangent points are going to be called T. We're only going to focus on one such tangent point. And what's special about this is if we select a point simultaneously on the plane and on the cone, for instance, this point, when we connect the origin and this special point P, we get a generator of the cone, a ray from the origin through P. And of course, there's going to be a corresponding tangent point, T. In this case, PT is equal to PF. Since the set of all such tangent points T is also located on the plane that is parallel to the generating plane here, then that means TH is constant. And the angle here is constant as well, so PT is going to be a constant value. Thus, TF is also going to be a constant value. So that justifies that the distance of a point on the circle to the center is always going to maintain the constant value. Okay, now this is especially inspiring when we change it a bit, because what is going to happen almost magically is the 2 points get separated. The 2 points I'm referring to right now is these two, the tangent points of the circles and the ellipse. In this case, let's study what is going on here. Again, let's take a point, and if we select the generating ray through O and through the origin and P, we will get again two tangent points, T1 with the gray circle and T2 with the purple circle. In this case, again, the same argument gives that, let's call these F1 and F2. The same arguments gives us PF1 is equal to P1, and PF2 is going to be equal to PT. In this case, again, all such T1 is going to lie on the same plane, and all such T2 is going to lie on the same plane, parallel to each other. So what that means is T1, T2, in this case, this length, is going to remain constant. What that means is PF plus PF2 is going to remain constant. So that is our conclusion for the ellipse. If we temporarily remove the circles, we will have a clean view of the ellipse and the two special points F1 and F2. Any point P on the ellipse to the distance of these 2 points added together is going to be a constant value. What we call these 2 points are the foci, the plural of focus of the ellipse. So F1 and F2 are the foci of the ellipse, and PF1 plus PF2 is going to be a constant value. Let's skip parabolas for now, and let's take a look at the hyperbola. Actually, you can arrive at exactly the same argument using the same circles here. So I would like you to do this yourself. I won't go into details right now, but essentially the conclusion is the absolute value of the difference of these two, of PF1 and PF2, is going to be a constant value. And again, let's visualize where the foci are for the hyperbola. You can see the 2 points, the red one and the blue one, moving just near the bottom of the hyperbola. And now it's time for us to look at the trickiest, which is the parabola. In this case, the second branch down below is going to disappear. So we have to study only the upper branch. Let's see. Now let's take a point somewhere here, P. on the parabola. The distance PF is going to be equal to PT. And the T is essentially the tangent point that lies on the origin, and P that is tangent to the sphere here. I don't know if you can see this clearly, but there's a sphere. Yeah, here you can see the outer rims like this. Now let's see what we can do. Because this time, evidently, PT is not going to be a constant value anymore. The length is always changing as P moves around. Okay, so in this case, let's say the point P, let's say it has a height of PH. Then PT is going to be equal to PH divided by sine of theta, right? This is our expression for PT. Now let's see what happens when we think about a very special line here, which is this line. So this line is defined to be the intersection of the plane where the set of the tangent points are, the tangent points of the circle, of the sphere, and the cone. And simultaneously, it is intersecting the blue plane. So in this case, for any point P, we can take the perpendicular line of P to this special line. Let's call it L for now. So what is the length of PQ? Well, remember, both P and Q is on the blue plane. So the angle between PQ, that looks like this, and the xy plane is going to be theta. The angle between PQ and the plane where L is positioned on is going to be theta. So remember, L is simply the intersection of another plane where the set of all t are located. And we also know when we take the point P down to H, this is the same pH that we previously had. So in fact, in this case, PQ again is equal to pH divided by sine theta. Recall that PT is also equal to pH divided by sine theta. So PQ is equal to PT. What this means is, since PT is equal to PF, so any given point P to the focus, F, is going to be equal to that special line. In this case, the special line is called directrix. Let's write it down, directrix. And this distance to the directrix, D, is going to be equal to PF. So PF is always equal to D. And this is the true focus directrix definition of a parabola. The parabola we previously learned about, which is y equals ax squared plus bx plus c, is not the true definition of the parabola. And that is all for the four shapes. To conclude, we have covered the four different types of plausible shapes of intersection. And in this session, we talked about the geometric meaning. And in the next session, we'll talk about how we can actually represent them on the coordinate plane. And of course, you might be interested in why I'm claiming the last shape we talked about is actually a parabola. How can it correspond to the y equals ax squared plus bx plus c expression? As for these mysteries, we will visit them the day after tomorrow. If you don't want to miss out on these fun math stories and exploration, don't forget to leave a like and click that subscribe button. I will see you in 2 days. Bye.